All right, so this is what we were talking about last time, was exceptions. If I'm writing the code in the past to convert strings to integers, and someone in the future, like you today, writes the code to convert a string to an integer, but you give it something that cannot be converted to an integer, what should I do in the past? Should I make the program crash? Should I just ignore it and carry on? Should I ask the user again? Like, how could I possibly know what solution works for you in the future? I can't. That's the problem we're trying to address with exceptions. Really what I'm saying here is what I can do, however, is raise an exception, which then communicates to the programmer using my code in the future that they have to specify what to do in this exceptional situation. Like if you're using my code, great. Now in some programming languages it really forces this. In others it's not forced, but you really should do it. Where if you're using my code and my code can be misused or something funny can happen, like in this example I'm about to show you. Divide, right? Well, what happens if someone tries to divide by 0? Well, I can raise an exception. In fact, there's a built-in exception type called a zero division exception that we could use in this particular example. You can make your own type of exceptions. There are some like general cookie cutter ones that you use. For this particular case, there's one that would use zero division error. And I can give with this exception, I don't need to, but I can give like a little like string that's a message. This is what you see, like array index out of bounds, index error. You tried to access index 11, but it doesn't exist, right? That's like the message. Here I just got a little string, whatever, nothing. But if b is 0, raise this exception. But in all other situations, just carry on, just do the division, easy peasy. So then this goes to the example. If someone uses this code and a 0 was provided, what do we do? What should we do? So this is entirely up to the programmer who's using my code. I'm the one that wrote this, and then you're going to use it. You're going to use my code. And then you, for whatever reason, you came across a situation where you passed as the second parameter a 0. And I need to raise an exception. All I can do is raise an exception and be like, something funny happened. Deal with it. Because I cannot possibly know what you want to do in your situation. I can't. I can't read your mind in the future. So this is the simple example of if b is 0, just raise this exception. We can even, if you're using code that can raise an exception, you, in the future, can catch the exception. Where, okay, I'm going to use this function, but if something exceptional happened, it's kind of just like an if statement. If something exceptional happened, here's how you're going to deal with it. And I'll show you the code to do that. So this is an example of some code that can raise an exception if something funny happens. And then this down here is an example of some code that is going to, well, I'm going to show you various examples of code that will catch the exception and then handle that exceptional situation in different ways for different circumstances and different needs. So the whole point here, like I've been trying to hit, is this function divide, let's say it was written in 1991, and you want to use it today in 2024. Okay, that's a while ago, 33 years ago. When you're using it today, you end up calling the function 9 divided by 0 for whatever reason. And this is going to be a problem for obvious reasons. You can't divide 9 by 0. So what should the original programmer in 1991 do about it? They can't. They don't know what you want to do. You're the one trying to use the function today for your needs, so you need to define what you want to do. How could the programmer know what you intend to do 33 years in the future when something funny happens? It's stupid to ask that question. Obviously, there's no way to know. So we have this messaging system, exceptions, as a way to pass that information around your program. What the original programmer can do is add some special code that says something funny happened that lets you know in the future, today, I know in the future today, I was talking from 1991. The person from 1991 can let you know today that something funny happened. And then it's up to you to decide what to do about it. Because what should happen? If you're dividing by 0, should the program crash immediately? Maybe. Maybe this was like it was reading input. Your program was reading input, and it just so happened to read a 0 from the input for whatever reason. So just read the input again. There, maybe that'll solve the problem. Or maybe you should just ignore it and carry on as if nothing happened. And this is all really dependent on your specific needs. If you're using a function that may result in an exception, you can write code such that you can try to run the code. And if something funny happens, like an exception was raised, you can catch, or here the syntax in Python is called except. Well, let me just show you with the example. Here's my code. I'm going to try the following code. And the code in that block might cause an exception. Like if I call, like maybe in that try, I say try to divide by 0. If everything was fine, if I didn't divide by 0, it would carry on as if everything's fine. It would run the try, it skips everything in the except, and it would continue on the runs regardless. If the exception was raised, then the except situation, that code runs. It's just like an if statement. If everything's normal, run this. If something funny happens, run this. Like that's like what's going on. So here's the general idea. My code, this is some example. I've got some function, my code. I'm going to try to run some various lines of code. They could be function calls. I don't know. Doesn't matter. The point is that code might raise an exception. If it doesn't, then whatever. It just carries on and it's fine. If it does, it stops doing what it's doing and it jumps down to the except block. Assuming, by the way, the sum error types match, but more on that in a moment. And then if the exception is raised, all of that exception code, in that except block will run. This is the well, what are you going to do about it? If something went wrong, what are you going to do about it? That's where we're going to put the what are you going to do about it. The above example, the code in the try would be something that may cause an exception we want to deal with. If it turns out the code does raise an exception, the code within the except block runs. If no exception arises, then the except block is skipped, just like an if statement. So any questions so far? This is still rather abstract, so I'm going to give you concrete examples in a moment, but do we have any questions so far? Yeah. The try, it's going to start running that code regardless. The try is there to match up with the except. Basically, the except part is the except needs to be following a try. So this is some code that could cause an exception. It's going to run regardless. It's going to try to run regardless. So it goes try. Oh, okay. And then it runs that regardless. And if nothing happens, if everything's fine and it runs all that code in the try block, it skips the except block and it carries on in the runs regardless part at the bottom. Yeah, one sec. If it's running and then along the way something funny happens, it stops, it jumps down to the except, and then runs in there. And that's where we're going to put the well, what do you want to do about it? Yeah.
If you're nesting this, say with an if else statement or a loop, are you trying to put the if your loop inside the try and then a separate loop for the except?
Well, that would be very dependent on what you want to do, but maybe after we see some examples, that might kind of clear things up for you. And ask again after we see some examples, if it's not clear. Other questions? Yeah? Not necessarily. If I was calling some code that I knew might raise a zero division error, I would write zero division error here. If it was, there are a bunch of pre-existing exception types like value error, index error, runtime, there's a lot. And there's actually a hierarchy where there's like runtime errors. And like, well, within runtime, you have like a value error, a type error, they're all runtime errors, but they're all a little different. And you can have like a hierarchy of how they're set up. And the hierarchy is important, but we're not going to get too much into those details right now. But it is possible, although just because you can doesn't mean you should, because a lot of the pre-existing exception types are sufficient for what we need. You can go and define your own, like a my assignment 3 maze exception. You could, don't, but you could, and then you could specify whatever you want in there. It's also possible that the code in that try, what if one line might raise a zero division error and another line might raise a value error? Well, what you could say is, well, if the code in the try raises an, like you can end up having like except value error, except zero division error. And you do two different things depending on what type of error you saw. Or you can do the same thing and you would say except some error or value error. So there's a lot of flexibility there. But now we're getting a little too much into the weeds. That's not important for us right now. But nevertheless, there are answers to those questions. Recording, right? Good stuff. So example 1. There exists a special value for floating point numbers in Python called nan, not a number. That's what that means, N-A-N, not a number. Which means, yeah, not a number. A reasonable way, so basically you can have something that is a float. Okay, you can have a value in your computer that is a float. You ask it, hey, this specific value, what's your type? It'll say float. And you say like, well, what's its actual value? Is it 0? Is it 1.72121111? Is it 100 million point 7? Well, you can have something that's actually like its value is not a number, but it is a float, which is weird, but there's purposes for that. Well, let me show you. Actually, it's funny. I'm trying to remember how I do this. Equals float nan. Is that how I do it? It's been a while since I've done this, actually. Probably the last time I did this was about a year ago. Yeah, perfect. Nan. So you're like, oh, well, it's just nan. It's a string. No, it's not. It's a float. But like, I can't say like a plus 4. Well, I guess I can. But like, what's not a number plus 4? Still not a number. So like, this not a number is a special value that exists for floats. It's still a float, but it has a special value that's just like, ugh, you got a number back, but I can't really represent it or deal with it. So, without going too much into the philosophy of what is not a number, we're not going to do that, but you can imagine, well, it's kind of like, you can kind of think of it as like an undefined or something, right? Like, well, you get a number back, but I don't know what the hell it is. So if you divide by 0, I think it's entirely reasonable for someone to say, okay, I'm going to try to divide by 0, and if it ever happens that they divide by 0, what we're going to do is we're just going to say the result is not a number. We're not going to crash. We're not going to like carry on as if everything's normal. We're not going to try again. We're just going to assign it that special value, not a number, and then carry on. That's what we're going to do. So if I were doing that, here's what my code would look like. I've got some function a, b, and it returns a float. This function should be returning a float. Good thing not a number is a float. So if I say try, get the quotient of divide a and b, and if I ever see a zero division error, I'm going to assign quotient to be not a number. I guess it doesn't matter if it's uppercase or lowercase because the example I showed, not a number, was lowercase. It doesn't really matter. I'm going to assign it to be not a number and I return it. So Most of the time, whenever we're not dividing by 0, we simply return whatever the quotient is, whatever the result of the division is. But in the off chance we ever see a 0 division error, we just sneak in and be like, okay, the answer is not a number, return not a number. That's an entirely reasonable thing someone could do. So this is one example of what one can do in that situation. Example 2. Consider a program that's requiring the user to input information with input, which is already a mistake, but whatever. You're using the input function. So look how I have it here. I'm saying, while true, so I've created an infinite loop. I'm going to say, read the data. Data is, well, give me some operand for division. Operands for division, I split it, I turn them into floats. And then I'm going to try to do the division. If I can do the division and everything's happy, I'm going to finish with that special line. Notice on line 8, there's a key word there that you might never have seen before. Raise your hand if you've never seen break before. Perfect. Well, there's a special keyword called break. To be clear, not knowing what break is doesn't limit your ability. Anything you do with a break, you can do without a break. It doesn't really matter. But we've got a break. Break means stop looping. Basically, create an infinite loop, and if we ever do the division and it's happy, break out of the loop. If we ever do the division, and on line 7, quotient is like, we raised an exception. We jump down, we skip the break, we immediately jump down to the exception, and we say, can't divide, try again. And the loop will continue to be an infinite loop. And it'll go over and over and over again until the person actually enters the correct values.
Does it break all loops or just the most nested one?
It'll break the most nested one. So you might have to have break, 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 break. But if you're doing that, you probably shouldn't be doing that. You probably could code it cleaner. Arguably, what I could do is I could set a flag variable and then go back up to the loop. But this, I think, makes it a little bit more obvious. So this is an example of, so the first one, to be clear, we divided by 0. Uh-oh, what are we going to do? Just assign it not a number and carry on. This example is, you divided by 0, try again. Do it again until it's happy. So 2 entirely different strategies. One is just assign it not a number. The other one is keep trying until it works. Yeah?
When you say not a number, here you have the ends capitalized.
It doesn't matter. I'm actually surprised it doesn't matter. Apparently it doesn't matter. Nan. I guess, yeah, they really don't care on if it's uppercase or lowercase whenever you're making a not a number. I literally found that out today, right now, yeah.
What's the use of having a float that
There's a lot of uses, one of which is this. It's a way to, and it can make the math happy. There's a lot of reasons, and without coming up with a series of complex examples to demonstrate to you, let's just not worry about it. And just go with trust me, there is. Yeah. I saw a question over here, yeah. It's kind of like infinity, but there's also infinity. Yeah. So there is an infinity as well. And see, a plus 4, well, it's still infinity. So there actually is a difference. So one might argue, well, as you divide, in the first example, as you divide by numbers that are closer and closer and closer to 0, you get a number that's bigger and bigger and bigger and bigger and bigger, right? So maybe it would be entirely reasonable to not make it not a number. Maybe you should make it infinity. Fine, do what you want. I was just showing you an example. As far as I know, dividing by 0 is still undefined, so it's undefined. So to say is it like infinity? It is like infinity, but it's different because as you can see, there is in fact a difference. That's fun. And of course, we all know infinity plus infinity is still infinity, right? Cool. Ooh. It's not a number. I love it. I love it. It's not infinity. It's just not a number. That's Python's way of saying, like, shut up. All right, cool. So what do we do in this example? Well, we just keep trying. Example 3. It may be the case that if the function causes an exception, our program should stop running immediately. There are several ways to make your program crash. An easy way is to call this exit function. You just call exit and the program will immediately stop running. So try to divide by 0. If something happened, well, just stop immediately. Maybe it's doing some calculations on how much radiation to apply in a medical procedure, and it comes up with a calculation where it tried to divide by 0. Stop. Stop running immediately. Something went wrong. Do not act like give the wrong dosage of radiation to people. Okay? Alternatively, I mean, if you have an exception that's thrown and never caught and dealt with, it will crash the program anyways. But using exit is arguably a little cleaner. And then sometimes the exception might be entirely inconsequential for your purposes, that if it's ever raised, like maybe you have a situation where your program is rapidly reading input from some sensors for calculations, and a divide by 0 is likely caused by some sensor precision issue, where like it measured a value close to 0, but the sensor it's not a very good sensor, it just read it at 0. And if that happens, whatever, ignore it. It doesn't matter for our needs. So it may be entirely, like it's so periodic and uninteresting and whatever, we just ignore it. So we could say, try quotient. If we ever try to divide by 0, pass. Pass is a special key, another special keyword in Python that means like do nothing. You might say, well, why do I even need to write pass here? We've got accept 0 division there. Can I just leave it blank? No. Whenever you have an indent, you have to have at least one line of code in there. And if you're like, but I don't, then you write pass. Just be like, shut up. I know what I'm doing. Yes?
What if you just have an indented comment? Does that count?
I don't know. I don't believe so. I think it has to be like a runnable line of code. Now, you could test it real quick and let me know. But I don't truly know, but my guess, my gut tells me you'd like a pass.
Comment space usually is compiled.
Yeah, I assume so, yeah. So why care? Well, which of the above examples is the correct one? Well, that's a stupid question because it really depends on the situation. And the point is, like I've been making this whole time, the point is the programmer in 1991, look, these are just 4 examples. There's a lot of examples I can give you on different things you can do. The programmer in 1991 doesn't know which of these 4 examples you should do in your situation, though. And there's more than 4, but they don't know what you want to do. If your program is calculating how much radiation to apply to somebody, and something funny goes wrong with that calculation, stop. Don't run. Crash the program, please. Try again. If your program is keeping your helicopter in the air, don't crash, keep running. Like, what do you want to do? It depends. In 1991, they don't know. So we have this idea of exceptions, where it's a way to pass information around in your program. The information is something funny happened, you got to deal with it. And it's actually kind of interesting because exceptions kind of provide a way to separate, like, what's the normal operating procedure of your code? And like, what's the okay, in case of emergency, weird situations, here's what you do. It actually provides like an easy way to have a separation between like the normal running logic and the like special edge case weird situation logic, which is also nice too. It didn't work? Perfect, perfect. So ultimately, exceptions are useful because they allow programmers to pass info around and communicate through time. In a weird way, it's true. They allow us to deal with exceptional situations effectively, and they provide a nice logical division between normal code and exceptional code, like I was just saying. If we go back up to here, let me show you some. I'm trying to think. I'm not going to go into more detail on this because the point of what I'm showing you here is you need to be familiar with exceptions. They're going to come up, and they've already come up for you. Now, actually, let me hit pause. There are some types of exceptions that you really ought not to ever deal with, right? So far, you've written code for things like indexing an array. Who here has ever accidentally indexed an array out of bounds? Usually, you're not catching those exceptions. You're not putting any indexing of an array in a try-catch block. You don't do that. That's usually like programmer error. A lot of the exceptions that we might want to deal with are going to be more like calculation and sensor input data errors. Not like programming error, but like data situations. So there are some types of exceptions you don't ever really want to bother ever trying to catch, like index out of bounds issues. But there are exceptions out there that, yeah, we would like to try to catch. Like maybe a zero division error makes sense in some situations. It's hard to come up with like a broad, here's the rule, because it's always like situational, but be aware of that. I don't want to go too far into the weeds. Exceptions are definitely going to be more of a topic in 162. They're still very important, don't get me wrong, they're going to come up. But this is about the level I want you to have an idea. In the same way with file I/O. Like I said with file I/O, I want you to be aware enough that you know what you don't know, that you can go find out the answers when you need to know. Same thing with the exceptions. I told you enough that you have a sense of what they are, and you know how to ask questions about them such that you can go and answer those questions. Last chance? Thoughts, concerns, comments, or anything about exceptions? Cool. All right. I'm going to show you an example of an interesting type of section, or exception. When I hit run, what's going to happen? Take a moment, look at this code. Don't shout it out loud. I want you to take 20 seconds, look at this code, and come up with an answer in your head. There's no trick here. I'm not playing a trick on you. This code is going to do exactly what it should be doing based on what we've learned so far. I want you to have an answer locked into your head. Commit to it. Raise your hand if you have an answer locked in. I'm not going to ask you to answer. I just want you to know. I want to know. Okay. For those of you that don't, come on. Commit to something. There's no trick here. What does the code say? That's all you can ever do is what does the code say? To be clear, that nan is not related. That's from the previous run, clear. Who wants me to run it? Huh. it seemed to have run, and then at the bottom we get this recursion error. Maximum recursion depth exceeded while calling a Python object. That's interesting. But until then, the output, what's it doing? Well, it's just counting. Who here had counting, or just like printing numbers out in their head? Who here, raise your hand really high if you had that. Raise your hand if you were wrong, because I'm curious what you thought it was. What did you think it was going to do? You thought it was going to do nothing. Did anyone else have it? What did you think? You thought it was just going to be 0? Okay. Anything else? Any other ideas that were terribly incorrect? I won't actually make fun of you. I'm just, having fun. No? So why? First of all, let's make sure this makes sense. What does the code say? There's 4 lines of meaningful code here. I've got a function definition called uh-oh, and it takes a parameter. And what do? It prints it out, and then it calls the function uh-oh, and it gives it the argument of whatever the value of a was, plus 1. Like, obviously, I'm not crazy. I recognize where this looks a little weird. You've got a function wherein the definition of that function makes a call to itself, which is weird. Let's see if we can make sense of it by what's happening on line 5. I call the function uh-oh with 0. So let's put some actual numbers here. A is 0. So when I print out A, I see what?
0.
And then I call uh-oh with a plus 1. If a is 0, what is a plus 1? 1. So we call the function uh-oh, and I give it the argument 1. So we jump up. A has a value of 1. I print out A. What do I see?
1.
What's 1 plus 1? 2. We call the function, we print out A. That's 2. Add 1, 3. Call it again, 3, 4, 5, 6, 7, 8. It just runs and counts. In fact, maybe it's obvious to some of you in here, hopefully all of you, it's just a loop. It's just like looped. There's no loop there though, but it seemingly looped. That's interesting. However, we do have a problem. The problem is the fact that this program actually, it crashed though. It raised an error, an exception. Yeah.
Is the error from Python or Google?
It's from Python. Well, both. It's Python though, Python. It's Python. We got an error from Python. This is a very special, computer scientists have a soft spot for this exception. Now, in Python, we gave this exception a slightly different name than what it's commonly known as. Does anyone know what this exception is commonly referred to? It's a very famous exception that most of you in here have heard of before, but you've probably never connected the dots. And don't yell it out, I just want to know. Does anyone in here have an idea of what this exception is actually usually referred to? You kind of have an idea? Anyone else in here maybe has an idea? I won't put you on the spot. Maybe, yeah. This is commonly referred to as a stack overflow exception. It's a stack overflow. Who here has heard the phrase stack overflow before? Yeah, probably. If you have Google and trying to program, you'll find Stack Overflow. It's a common website where people ask questions about programming and whatnot. Stack Overflow. The details on what the hell this really means are a little bit outside the scope of the course. It's rather simple, but it's outside the scope of the course. The problem with what I did is I effectively made an infinite loop, because it'll never stop. But I can make it stop. By doing something like if A equals 100, there. It'll only ever go from 0 to 100. I can make it stop by having the function just okay, well, then don't call yourself again, just stop. So I can make it stop. Now, if I made this like 10,000, Python's still going to be like, no, stop it. And there is a reason, but the reason for this is actually more of an engineering, like design limitation of how our computers work. And that's actually an interesting thing to hit on, is, we have to be careful about what we consider a computer. Because there's a lot of things out there that are computers by definition. And I'm not playing a game of like, technically, a safe lock is a computer. And I don't mean like I mean like an old school, that's a lock. It's something that can receive inputs, has some states, and can produce some sort of like functionality or output. It's a computer. And I'm not being like, technically it's a computer. I mean like, no, it is like a bona fide, straight up, there's no weirdness to it. It's a computer. It's just the problem is, in today's lingo, when we say computer, we almost always are thinking of those boxes in front of you, right? So a computer is a far more general idea. And computation is a far more general idea. And the way we go and design and make computers that we're like designing and engineering to solve problems for us, they're designed by us. But there is like a fundamental like universal truth about computation that is limited by how we design our computers. And this is an example of one of those limitations. Bless you. Anyways. Any last questions, thoughts, or anything about this? This, by the way, is very, 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 very much related. If you got a sense of this already, good. If you didn't, that's fine. You're probably pretty normal. But if you had a sense of connecting the dots of what I just showed you here with when I appended like the list to itself, these are very related ideas. So if you thought of that already, you're like, it's kind of like when you like appended the list to itself, which really was just a reference to the list, but it was self-referential. Yeah, clearly this is defined in terms of itself, right? Anyways. I think it's kind of fun. And also, here's a funny thing about this. Bless you again. Or was that her this time? It wasn't you. Who was it? It was you. Oh, cool. You can, yeah, okay. My ears aren't that good. When it comes to, yeah.
So if we have a list like a list in itself, right? If we go deep enough into that like loop, will it also get mad?
It would depend. That's a big, the easy answer is no, but it would depend on like how I went, like going into investigating how deep it went. Because when you define the list where it has a reference back to itself, it's static. There's nothing about, it's just like, oh, okay, and it contains a reference back to itself. In the same way that like this is static, it's just, it's defined in terms of itself. It's not until like we go about like running it. And with that loop, if we wanted to go like keep referencing it, if I kept referencing it with like an infinite loop where I said like while true, it would be fine. It would run forever, it's fine. But if I did it with a way something like this, I would then have an issue. The issue though would not be caused by the loop or the list, but by how I was iterating with this strategy. And this strategy right here, where you have a function defined in terms of itself, is called recursion. We kind of talked about this before. This was like as suggested. It's like when looking at this, right? You've got like the thing inside the thing, inside the thing, inside the thing, inside the thing, inside the thing. Forever, 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 forever. One thing really cool, I think, about this, like I looped. Effectively, I looped. But there's no loop here. There's no for loop. There's no while loop. But I effectively looped. I iterated. I repeated some process over and over and over again. And I know that when you're a new programmer and you're learning to program with a language like Python or similar languages, loops feel natural in terms of like the syntax and how we write our code. But when it comes to like nature, And when processes in our universe and in nature are like iterative, the way they iterate, the way they say like loop, is more analogous to this than a for loop. Things end up being defined in terms of themselves, and that's how it can keep repeating a process over and over and over in nature. It's a far more like natural way. That's really not the right word to use, but I'm going to go with it. It's like a much more like pure, that's also not the great word to use, but let's say like a more pure way of like iterating. It's more like what you would expect to observe in nature. Things can happen over and over and over again because these things are defined in terms of themselves. Like, think of just like how like crystals are growing, right? Like if you have like ice crystals growing and they generate those interesting fractal programs, there's no for loop. It's just like, how do these things crystallize? Well, they crystallize by connecting the dot with, by connecting to itself over and over. It's kind of how these processes happen. Pardon? Yeah, maybe that's a good way to word it, yeah. Any other last thoughts, questions, or anything about this? Yeah. There are ways you can change it. It's not that this is limiting you into, I can try to give you a little bit of insight into what's going on. In your computer, whenever you have a function call, as by how it's designed, whenever you have a function call, we have something called, you know what? Maybe I have a GIF. It's in here somewhere. Huh? Oh, come on, do I not have it? Shoot, I really thought I had the GIF. Okay. Yeah, okay, here we go. So there's something called like the call stack, which basically is every time you call a function and a function calls itself, like let's say I realize this is Java, don't worry, it's not going to throw you off. I have a main, when I hit run, this is the function that your program calls. But you'll see that main calls function 1, and in function 1 calls function 2 and function 3. In function 2, it calls function 4, and function 3 does whatever, and function 4 does whatever. The point is I have functions calling other functions. And the way this works is, okay, main gets run, it calls function 1. Then it calls function 2. And you'll be like, but it also calls function 3. Yes, but it calls function 2. It goes and does everything with function 2. When that's done, it comes back and then carries on. And this is all kept track of with something called the call stack. And that would call main. Main calls function 1. Function 1 calls function 2. Function 2 calls function 4, which finishes, returns, finishes, return. Function 1 calls function 3, finishes, returns, returns, returns. We're done. When you have a function calling itself, you end up having, this just goes on, and on, and on, and on, and on. And eventually, the computer goes, you've had enough RAM, you're done. It's not that you're limited in terms of how much, you're not limited in terms of how many recursive calls your function can make. You're limited by like how deep. Because like if your recursive calls can go and come back and go and come back and go and come back, but you just can't keep going on for 100, that's where you end up having issues. So you might, I'm certain there are circumstances where you need more. And you can actually go in and tell Python, increase this, like the stack size, increase what the hard limit is. You can say that. But chances are you really don't need to for most normal people. Though we're here, and so clearly we're not. Yeah?
So we can call a function before defining it?
You can define a function. No, what do you mean? Do you mean like how, wait, I called function 1 before it was actually defined here?
Yeah, and in function 1 you call function.
Yeah, this is entirely fine, and this will work in Python too, but it's because if we have like 2 paths, where the program goes, it reads everything, and goes, okay, everything exists, it checks out, I can run it. In some older languages, this would be like, I don't know what function 1 is, right? But it's because like all of this is written at once, I hit run. And then it could do like 1 pass, 2 pass. Good question and good observation, but at the end of the day, yeah, they figured that one out for us. Yeah?
Are there any languages people actually use where that wouldn't work?
Yeah, like old school C, yeah, that could be a problem. Yeah, I know, right? But yeah. And everyone who's got hired to deal with bank legacy code written in Fortran, I'm sure there's a problem there. And yeah. It's funny. It's funny. You have probably a few people in this room will get jobs as software engineers, and you're going to be working with a programming language that died a long time before you were born, but you're stuck using it because Bank of Nova Scotia still uses it with the code that was written 50 years ago by people, and because at that time people did not know how to write code good. And so, good luck. Yep, there you go. That's the dream, right? Good news is they'll pay you big bucks for it, though, so, you know. Last chance for questions? All right, well, I'll see y'all Friday.